So how many of you were at the talk yesterday? Because this will be the methodological aspects of the talk I gave yesterday, which were was on the other hand focused on more the application side. So this is a joint work with some PhD students, current and past PhD students. Antonio and Yuri are current PhD students. Michele, Elena, and Dono are past PhD students, as well as Francesco Dendi, and the other principal investigator of the project is the colleague and friend Alessandro Laio. So they are physicists based, well, physicists and data scientists based at Trieste in Italy. They do great research, and we've been jointly collaborating over this research line on intrinsic dimension. Before I met them, they were not Bayesians. Now turn them into Bayesians. And you will see that there are some aspects that still survive that are not inherently Bayesians, but I'll talk about all of them. So for those of you who were there yesterday, you know the answer to these questions. These are data points collected in 3D, but the coordinates of those points are not free to fill in the three-dimensional space, because they are forced to live in a two-dimensional manifold. So depending on how you look at the data, and specifically if you have the right perspective, you realize that those data are constrained in a Swiss roll space. So there is a deterministic mapping between X and Y, two-dimensional coordinates, to three-dimensional coordinates. So the question that I will try to address today is, well, we know that data has been collected in capital D equal to 3. The question is, what is the intrinsic dimension of the data? Which in the case that you just seen is 2. So we call 2 the, as I said, intrinsic dimension of the data. And the question is how to estimate this quantity. And the point is that while in the previous example, all data points were constrained in a two-dimensional manifold, sometimes some subset of the point are free to move in the original embedding space, in this case, 3. Another subset is constrained in a two-dimensional manifold, and maybe another subset is constrained to live in a one-dimensional manifold, so in a line with or without noise. So as you see in this other example, here we have 5,000 data points. The first 100 are on a Gaussian in a one-dimensional space, and then the second 100, the green ones, are generated from a Gaussian in a two-dimensional setting, and then the additional 1,000 is four-dimensional, then 5, and the last red points are generally living in a nine-dimensional space. So in a setting like this, we would like to estimate how many submanifolds there are, which points are embedded in which submanifold, and what is their intrinsic dimension. And we want to do this always with a Bayesian perspective, or at least being able to assess the uncertainty around our estimates. So yesterday I showed a bunch of applications, mostly related to life science, with data as in proteins, fMRI data, gene expression data. We look at the COVID-19 pandemic evolution. This was joint work with QUT. I mentioned the basketball data, which I will not talk about because I understand it has been talked a lot. But this was also joined with Edgar and colleagues from QUT. So what I will focus on today are two specific applications of intrinsic dimension computed on the output of an MCMC simulation, and intrinsic dimension computed on the different layers of a convolutional neural network. Because I think those two applications are very enlightening on the potential of using intrinsic dimension in settings other than specific applications. So, and today I will focus more on the methodology. So yesterday I sort of gave an idea of what is the 2 nearest neighbor estimator. Today I will talk about the generalized ratio of intrinsic dimension estimators. Those 2 estimators work well if your data points are all constrained on a single submanifold. On the other hand, if you have more than one submanifold, you should use the Hidalgo or the Bayesian parametric version of Hidalgo. And I will tell you about these 4 estimators and the pros and the cons of each one of them. I will focus on the continuous version of this estimator, so where your data live on a continuous space. But we have also developed a version of the 2 nearest neighbor estimator and of the glide estimator that also work on discrete metrics, so where your data is discrete rather than continuous. Good. So let me formally define the intrinsic dimension. The intrinsic dimension formally is the support of the distribution that has generated the data. And in the literature, there are different approaches to estimate the intrinsic dimension. Some of them are projective methods or more related to the topology. The approach that we take is a nearest neighbor type of approach, and it's not the only one that is available in the literature. But most of the methodology in the literature, because comes from mathematics or physics, typically lack of a statistical estimation procedure and an uncertainty quantification, which is our added value as statistician. So formally, the idea is that we have a set of n statistical units that are collected in a d-dimensional space. And we assume that these x's are a realization from a Poisson process with an intensity function which is locally constant. So it's a locally homogeneous Poisson process. And I want to stress this locally homogeneous homogeneity of the intensity, because pretty much all other methods assume that the intensity of the Poisson process, or whatever process is generating the data, is globally constant. So we strongly relax this assumption. So given this data set and taking a unit xi, we look at the first and second nearest neighbor. So xi is the ith unit in your data set. And we look at the first nearest neighbor, the second nearest neighbor, and all other nearest neighbors. And we let ri1 to be the distance between the ith unit, which can be seen as a point in the d-dimensional embedding space, and the first nearest neighbor. So this is ri1, and then we have ri2, ri3, and so on. So ri is the distance between unit I and its Lth nearest neighbor, RIL, the Lth nearest neighbor, according to some metric. So any metric will do. So now that we have these distances, if we take 2 integers, n1 and n2, with n2 greater than n1, we can find the distribution of the ratio of distances between the nth2 nearest neighbor and the nth1 nearest neighbor. So this ratio of distances, which we call mu I, because we have a ratio of distances for each point in the data set, as a distribution which we can write down analytically and has this form. So this distribution, if you consider n2 equal to 2 and n1 equal to 1, so if you look at the second to first nearest neighbor, you get the 2 nearest neighbor estimator, and that distribution becomes a Pareto distribution with parameter d. So what's important in this distribution is that everything is known but d, which is the intrinsic dimension of the data. So the distribution of distances of neighbors, actually they don't even need to be neighbors anymore, of n2 to n1, as a closed form expression, and is only parameterized by the intrinsic dimension of the data. And this a special case of this distribution is obtained when n2 is 2 and n1 is 1, and becomes a Pareto distribution with parameter d. So in this specific setting, we have the 2 nearest neighbor estimator, which was the very first estimator that those physicists came up with. And because we have a Pareto distribution, we can estimate the parameter of a Pareto distribution either by maximum likelihood, and here's the estimator, and then we can come up with a confidence interval using the quantile of this Pareto distribution. Or we can be Bayesians. We put a prior on the unknown parameters. Here the unknown parameter is d, the intrinsic dimension, which is what we want to estimate. And we derive the posterior distribution because the prior gamma is conjugate to the Pareto. The resulting posterior is another gamma distribution with updated parameters. So if the prior is a and b, the posterior is a plus n is the number of points, and b plus the sum of the log of the mu's. And we can write down in closed form the posterior mean, which will be our Bayesian estimator, and find the posterior credible intervals, which is the Bayesian counterpart of the frequentist confidence interval. So when n is 2, and when n2 is 2 and n1 is 1, everything is available in closed form. We have a Pareto distribution, we have both the maximum likelihood and the Bayesian estimator available. And notice that if n, the number of points, goes to infinity, the posterior mean is asymptotically equivalent to the maximum likelihood estimator, which is what typically happens in a Bayesian setting. If you have more and more data, the prior information washes out. So what is the advantage of going from the 2 nearest neighbor estimator to the GRIDE estimator? GRIDE stands for Generic Ratio Intrinsic Dimension Estimator, which is what we are now currently using when we believe that all points are constrained in a single dimensional manifold. So the 2 nearest neighbor estimator only looks at the second and the first nearest neighbor estimate points and the ratio of those distances. On the other hand, the GRIDE estimator, you have the freedom of choosing n1 and n2. So for example, if n2 is 40 and n1 is 20, for every point, which are blue sample points in this data set, you look at the ratio of distances between the 40th and the 20th nearest neighbor. So what are the advantages and disadvantages of the original 2 nearest neighbor estimator and the GRIDE estimator? Well, remember that we assume that the Poisson process has to have local uniform intensity. So what does local mean? Well, in the 2 nearest neighbor, this assumption says that the intensity of the Poisson process has to be constant over the average distance of the second nearest neighbor. On the other hand, for the GRIDE estimator, it has to be constant over the average distance of the n2 nearest neighbor. So this is a stronger assumption. So the local uniformity assumption is stronger in the GRIDE than it is for the 2 nearest neighbor estimator. On the other hand, when we look at those ratio of distances, we assume that those quantities mu i's that we have for each one of the points in the data set are independent, and we form the likelihood by taking the product of the mu i's. Now, if 2 points share either the first or the second nearest neighbor in the 2 nearest neighbor estimator, this independence assumption does not hold because they have shared neighbors. And having shared neighbors happens more often if you're looking at the 2 nearest neighbor estimator than if you're looking at the GRIDE estimator. So it is less likely than 2 points share the 40th and the 20th nearest neighbor than 2 points in the data set share the second and the first nearest neighbor. So 2 nearest neighbor is better when considering the local uniformity assumption, and worse when considering the independence assumption. So the 2 nearest neighbor estimator, a ratio of second to first nearest neighbor, has the pros that the narrow neighborhood are more likely to respect the local homogeneity assumption. We have an estimator which is available in closed form, but this estimator is sensitive to noise in the data. On the other hand, the grid estimator has the advantage that 2 points are less likely to share the N2 and the N1 nearest neighbor. We do not have a closed form expression of the estimator, so we either have to do numerical optimization if you do maximum likelihood of that density that I showed you at the beginning, or we have to do MCMC if we are Bayesians. But on the other hand, the assumption on local uniformity is stronger. What we actually do is the following. So instead of fixing a value of N2 and a value of N1, and typically, as I said, we take N1 to be N2 divided by 2. We let N2 grow. So we take first N2 equal to 2, then 3, 4, 5, and so on and so forth. And for each value of N2, we estimate the intrinsic dimension. And so we get what we call the grid intrinsic dimension path. So here you see it in this plot as N2 increases, I get a different estimator of the intrinsic dimension. And eventually, this estimator reaches a plateau, and that's where we estimate the intrinsic dimension. So in this example, the intrinsic dimension will be estimated to this value, where the plateau is reached. So why do we reach this plateau? Well, because data often come with noise. So this is another three-dimensional setting. It's 3D, easy to visualize. So in this case, data is living on a one-dimensional manifold. So they're living in the blue line, on the blue line, but it's recorded with noise. So the points are around this blue line with noise. So if I look at this data too closely, so if I zoom in too much, we get the impression that the intrinsic dimension is 3. If we zoom out a little, as in the second circle to the right, we get the impression that the intrinsic dimension is 2. Only if we zoom out sufficiently far away, we bypass the noise in the data, and finally we get the proper estimated intrinsic dimension. So the intrinsic dimension goes from 3 to 2 to 1, and this zooming out of the data and bypassing the noise is equivalent to let N2 increase. So by increasing N2, I bypass the noise slowly. So the intrinsic dimension first decreases, then reaches a plateau, and then decreases again, because if you zoom out too much, everything looks like a point and has intrinsic dimension of 0. Good. So questions about the 2 nearest neighbor estimator and the grid estimator are welcome at this point, because then I will move to the setting where there's more than one manifold, where the data points are embedded. Yes?
Thanks, Antonietta. My question is about these estimators. Is there any sort of invariance properties to them? I say you transform the data in some nice way.
Can you repeat the question?
Yes. So the question is there some sort of invariance property? This is a very good question. Thank you. So typically, what we do before estimating the intrinsic dimension is rescale the data so that we sort of standardize them. So we rescale the columns of the input matrix. The intrinsic dimension is not invariance to the noise in the data. The sigma is in the data. So if you increase sigma, then the scale at which you have to look at the data to get out of the intrinsic dimension changes. But in a sense, it is invariant because, in a sense, our estimator, by doing this zooming out, bypasses the noise, and then at the end of the day, you get the same intrinsic dimension. But yes, the estimator is sensitive to the noise in the data. So in that sense, it's not invariant. On the other hand, it's not sensitive to location. So it's location invariant, but not invariant to scale. Thanks.
Thank you.
Yes.
One other question. When you've got a lot of intrinsic dimension versus N2, and you want to look for that plateau, is there a systematic way of doing that, or does it always have to be done sort of by visual observation?
Thanks. So the question is, when we get to this plot, do we have to do it visually, finding the plateau, or there's a better way of doing that? Okay, so the answer is, what we are working right now is a way of finding the optimal N2, the optimal zooming out, without violating the local homogeneity assumption. So instead of working with the grid, with the grid path, now, and I will talk about this at the end because this is ongoing research, we have the grid star that uses an N2 star, which is the optimal, the largest N2 that I can use without violating the local uniformity assumption. So that will bring us, hopefully, outside the noise and directly in the plateau. But thanks, a very, very important question. Because I also didn't like to look at plots and say, okay, where's the plateau? Because sometimes it's not so clear. So now we have the grid star estimator that bypasses this issue. Thanks. Yes?
So do you mean that, like, so we have to take care of estimate the value for N2 as well when we use the grid method, right?
Yes.
So it's like we have another parameter to be taken care of.
Okay, so the question is, do we also have to estimate the value of N2 when we use the grid? And in a sense, yes, and you estimate it by looking at the plateau. But now we have a way that we have the grid star that fixes the value of N2 to the largest value that you can use without violating the local homogeneity assumption. And that is crucially done point-wise, because there might be different values of N2 depending on where you are in the space, right? Because right now we have to fix a value of N2 for each point. And it might be that in some parts of the space where points are living, you have a different noise. Okay, so right now what we have is a N2 star I point specific. Okay, so this in the grid, yes, there's an additional parameter, but in the grid star, no, there's no more N2 to be fixed. We do it automatically through this procedure I will talk about at the very end, because this is ongoing research, it's not published yet.
Side question,
Sure.
like very complexity process to estimate the value, those value of N2.
Sorry, say it again?
So is it a very complex city?
No, not at all.
Yes,
Just
okay. It's just
So the question is, how complex is it to find the optimal value of N2? It's not complex at all. It's a likelihood ratio test in a sense, because we are testing an hypothesis of homogeneity of the, so it's a likelihood ratio test that you perform for each point. Good, thanks for the questions, very, very helpful. Okay, so now we move from a setting where we have multiple manifolds, each one with its own intrinsic dimension. So this is a typical picture. So here points are collected in a 3D embedding space. And we have 3 submanifolds, each one with its own intrinsic dimension. So in this setting, we want to estimate capital K, the number of manifolds, the intrinsic dimension of each manifold, and ultimately the intrinsic dimension of each data point within each manifold, and everything with the proper uncertainty quantification. So we have the 2 nearest neighbor estimator version for this general setting. We are working on the grid star estimator in this general setting. So this is ongoing research. Good, so we're now back to looking at the ratio of distances between the second and the first nearest neighbor. For each point I, we have mu I, which is this ratio of distances. We know that this ratio of distances has a Pareto distribution with intrinsic dimension d if all points live in a d dimension, lowercase d dimensional manifold. If you have more than one submanifold, well, simple, you use a mixture of Pareto distribution. So if you have k submanifold, the distribution of mu I is a k mixture of Pareto distribution. It's each one with its own intrinsic dimension, d sub k. So then we have the independence assumption coming into play. Okay, so we take the product over all data points. So the likelihood of the vector of mu's, and we have one mu for each one of the data points, is the product over the data points, and then the sum of Pareto distribution, where pk are the mixing probabilities in the Pareto mixture. So now, instead of having a single d to estimate, we have capital K intrinsic dimension and capital K mixing probabilities. So again, we can take either a maximum likelihood, a frequentist approach, and maximize the likelihood with respect to these two vector of parameters, or we can take a Bayesian approach. So we put priors on the two unknown vector of parameters, d and p, and we derive the posterior, which is the proportional to the product of the prior times the likelihood, as Bayes' theorem tells us. So what are the conjugate priors? Well, we take on each d a gamma prior, and on the vector of p a Dirichlet prior. Those are conjugate priors. And we then introduce these latent indicator variables, z, whose distribution is discrete over the values 1 through k. So if zi is equal to 3, it means that the ith data points live in the third manifold, and it has its own intrinsic dimension. So estimating mixture models in Bayesian statistics is something we know very well how to do. So we derive the likelihood, have those priors, write down the posterior, and we estimated the intrinsic dimension. So it seemed like a nice methodology, but we were getting estimators that were all over the place. So we realized that we were missing something. So we were needing to gather from the data more information than the one that is contained in the mu-i's. So after all, you can think of the mu-i's as summary statistics from the data that we use to estimate d. So we needed to enforce a local homogeneity assumption, not in the Poisson process, but in the manifold space. So here's the assumption. We had to assume that different manifolds are separated in space, which seems to be a reasonable assumption. Otherwise, we won't be able to estimate anything. They're all messed up and overlapping. And we have to assume that a neighbor of a point should be more likely to contain points sampled from the same neighbor. So if me and Carrie are neighbors, we are more likely than not to belong to the same submanifold. Okay, so this is a local homogeneity assumption of the manifolds, not of the Poisson process. So with this local homogeneity assumption, which we enforce by extracting from the data additional information, which is encoded in a n by n matrix, which is a neighboring matrix. So n is the number of points. I have this n by n matrix. Each row in this matrix, so the ith row, refers to the ith point and is all zeros except for some ones which are turned on corresponding to the first q nearest neighbor of that point. Now we have q, which is an additional parameter, but we typically set q equal to 3. So we have this n by n matrix with all zeros on each row except for 3 ones which are turned on for the 3 nearest neighbor. And this choice is a fairly robust choice everywhere in all the applications that we made. Yeah. So yes, it is an additional parameter, but we take q equal to 3. So with this additional information that we extract from the data, so this neighboring matrix, which is added to the likelihood and therefore enters the posterior, we manage to estimate the number of components, the intrinsic dimension, the number of manifolds, their intrinsic dimension, and assign each point to the proper manifold. Now, remember, we have a mixture of K Pareto distribution. So how do we choose K? Well, here K is another parameter, that identify the model. So we estimate this Pareto mixture and the resulting posterior distribution for different values of K. And then we can estimate the K with a model selection quantity, like, for example, BIC or AIC or your favorite model selection methodology. Lately, as a matter of fact, we use more clever ways that can be adopted when you do model selection in mixture models. So there's a paper that allows us to do that. I think Carrie's even co-author there, to do model selection in a mixture setting without having to estimate for each value of K. But the alternative solution is to let K go to infinity and our finite mixture model become an infinite mixture model. And so we go from the Hidalgo to the Bayesian nonparametric Hidalgo. So in this setting, we adopted the Dirichlet process as the prior of the parameter, and we modeled the intrinsic dimension. So I will not go into the details, but you know, there are standard statistical methodology within the Bayesian nonparametric framework that allows us to estimate this infinite mixture of Pareto distribution. So going back to the original motivating example, so this is very difficult because, for example, this one-dimensional Gaussian distribution is completely embedded in the two-dimensional green points. So the black points are mixed up with the green and part of them also with the blue, which are the 3 or 4 dimensional manifold. So this is a hard problem. So we used the BNP Hidalgo, and we were estimating the number of manifolds correctly, 5 manifolds. And here you see the green lines, which are the actual intrinsic dimension, and the red line, which are the maximum likelihood intrinsic dimension estimator over each group, which basically coincide also with the Bayesian estimates. So you see that for the points that are in the 9-dimensional manifold, those are the red ones, which are very well separated. We get it perfectly right. So all points, which are the last 1,000 points, are assigned to the proper manifold, and the intrinsic dimension is correctly estimated. And we also do a fairly good job for the second submanifold. But let's look at the first submanifold, the one that has intrinsic dimension 1. Well, we correctly estimate the intrinsic dimension. You see the red and the green line are almost overlapping. But some of the points, those points here that belong to the first submanifold, are assigned to the second submanifold. And similarly, some of the points in the second submanifold, those points here, are wrongly assigned to the third submanifold. And there are points in the first submanifold that are also wrongly assigned to the third submanifold. So those are the black points in here. Okay, but this is a very hard problem. And we were still very happy with the results because we realized that this is a very challenging situation. Okay, so I will now move to the use of intrinsic dimension to identify identifiability issues in your modeling framework. Okay, so this is a good time to ask questions related to the estimator where you have more than one submanifold. I didn't go very deep into the details because then it becomes tedious, but details are in the corresponding paper. And we basically just used standard Bayesian methodology to estimate mixture and to estimate infinite mixture to get out what we wanted. So everything worked out just fine without particular thinking, except for applying those methodologies. Okay, no questions from home either. So let me move on and use the intrinsic dimension to answer a very important issue that is there in a frequentist setting, and that Bayesian usually say, well, we don't care about identifiability because we have priors, but I think Bayesian should be worried about identifiability issues as well. So what is weak identifiability? It means that the likelihood has almost flat regions. Okay, and if that happens, it means that the data is not informative on the values of the parameters where you have this flat ridge. In a Bayesian framework, we say, well, that's an issue of the likelihood. As soon as we put a prior, which is even weakly informative, that flat region is not flat anymore because the likelihood is multiplied by the prior, and the posterior does not have any flat region anymore, and we're happy and fine. And we say we have solved the identifiability issue. But I think that also as Bayesian, we should be worried about the identifiability issue. So what happens? It happens that the marginal distribution of the non-identifiable parameters does not scale with the sample size. And this will impact the intrinsic dimension of the posterior distribution of the parameters. So if you have an identifiability issue or an almost identifiability issue, this shows up in the intrinsic dimension of the posterior distribution. And as I said, as Bayesian, we should be worried even about weak identifiability because that results in lack of posterior consistency. So let me show you a really easy application to explain you what we mean. So here we have two models, model 1 and model 2. Model 1 is a linear regression where we have 4 explanatory variables, x1, x2, x3, and x4, plus an intercept, beta 0. And we have an error whose variance is known. So it's just a Gaussian noise, 0, 1. So we don't have any parameter in the error to estimate. So if we're Bayesians, we put priors on the parameters, we get the posterior, and we can run our MCMC. Well, the posterior here is a well-known distribution, but let's pretend we don't know what it is. Well, specifically, we put very non-informative priors, so Cauchy prior with parameters 0 and 10 for each beta i's. On the other hand, model 2 is very similar. It's again a linear regression, except that we have, it's an ill-posed model. So we have twice the intercept, and we repeat twice x2, the second explanatory variable, plus x4. So in this case, there are some of the parameters that are not well identified. Specifically, I cannot estimate beta 0 and beta 1. I can only properly estimate the sum of beta 0 and beta 1, or the difference. So the sum or the difference is well identified, but each one of the betas is not well identified. And similarly for beta 2. So now on those two models, we run our MCMC simulation, even if we might not even need to do so. So we run STAN, which is an Hamiltonian no U-turn sampler, that returns 5,000 samples from the posterior distribution. Okay, now the posterior distribution lives on a 5-dimensional parameter space. So capital D, the embedding dimension of this posterior distribution should be 5 because we have 5 parameters and the Markov chain lives on a 5-dimensional space. But what happens? For the data generated by the non-identifiable model, because it's a simulated setting, so we generate data and then we use the data to estimate the parameters. So the data generated from the non-identifiable model does not allow to properly identify and therefore estimate all the 5 parameters. So this is reflected in the intrinsic dimension of the posterior distribution, which is not 5, but shrinks to 2. And 2 is the number of the non-identified parameters. So one of the 2 intercepts and one of the 2 slopes of x2 is not identified. On the other hand, we expect that the data generated from model 1 leads to a posterior distribution that has proper support on the 5-dimensional space of the parameter, if n is finite. And if n, the number of data points, goes to infinity, then because all dimensions scale with 1 over n, equally fast, the intrinsic dimension will asymptotically go to 0. But if we have a finite samples number of points in the sample, this is the real sample, we will see a 5-dimensional, that the posterior distribution lives on a 5-dimensional manifold. So indeed, this is the posterior distribution of the intrinsic dimension of the posterior distribution of the parameters. Okay? So we have the posterior distribution of the parameters that we get from our MCMC STAN output. And we estimate the intrinsic dimension of those points, and because we are Bayesian, we have the posterior distribution of the intrinsic dimension. We extract the intrinsic dimension to be 5, and indeed it is estimated to be 5 with fairly little uncertainty. On the other hand, if we do the same game for the M2 model, so we run the intrinsic dimension on the output of stan of that is estimating the posterior distribution of the second model, the non-identifiable one. Here is the posterior distribution. It's 2. So now, this is the intuition. As I said, the non-identifiable model, there are 3 parameters that are well identified. And those 3 dimensions of the posterior distribution are vanishing as 1 over square root of n and become negligible with respect to the 2 non-identified parameters, which do not scale with the sample size. On the other hand, for the well-identified model, if n, the number of points, goes to 0, we get a 5-dimensional vector whose intrinsic dimension is 0, but for finite sample sizes, we get 5 as a posterior distribution. So now we have an additional hypothesis test that we can do on the intrinsic dimension. So not only we can estimate the intrinsic dimension, but this is an added thing that we've done since I last visited the QUT. So we can do hypothesis testing on the intrinsic dimension, and we can do this both in a Bayesian setting or in a frequentist setting. Let's do it in a Bayesian setting. So suppose I want to test the null hypothesis that the intrinsic dimension is equal to the dimension of the embedding space, in this example 5, versus the alternative that is strictly less. Fine, we're Bayesian. We put a discrete prior on D, and specifically, not to favor the null versus the alternative, we put half of the mass of this discrete prior on 5, and we distribute the other half of the mass on 1, 2, 3, 4, on the other possible values. So we can work out analytically the posterior distribution of the intrinsic dimension. So here it is. And as Bayesians, we reject the null hypothesis if the probability of the null space, the space identified by the null hypothesis, is less than alpha. So I'm going to show you the results of this linear regression, but we have done the same for the GLM family, logistic, Poisson, and so on, with similar results. So for the well-identified models, this is the prior. So 5, 1/2 probability on 5, and the remaining probability spread out on 1, 2, 3, and 4. And this is the posterior, concentrated on 5. So the posterior probability of the null hypothesis is practically 1, so we accept the null hypothesis with great confidence. On the other hand, for the non-identified parameter, prior is the same. The posterior is pretty much point mass at 2. So in this case, we reject the null hypothesis that the intrinsic dimension is equal to 5. So we were very happy about this result. So if you have questions on how to use the intrinsic dimension for identifiability issues, I'm happy to answer. This is, again, an ongoing research line. So we're now actually trying to see what happens, and we've done this already, when we put some constraint on the parameters. So we have the non-identifiable model with, and we put constraints, and we see that we can regain identifiability. So the estimated intrinsic dimension goes back to what we expect it to be. But we are still experimenting on this. And we are writing these things up. Okay, I think I still have a few minutes. So this is the choice of K I was telling you about at the beginning to answer your question. So let me tell you a few words about an alternative way to estimate the intrinsic dimension, which is an indirect way. So in this paper in Science 2000, they introduced local linear embedding. So how does local linear embedding works? It finds the intrinsic dimension by trying to project the data on a lower dimensional manifold, and then computes some loss function and finds D as the intrinsic dimension which is the dimension where I project to that gives me the smallest loss of information, in a sense. So this local linear embedding, LLE, has 3 steps, basically. First, finds K, the K nearest neighbor of each point xi, and K is one of the parameters that they have to find or to fix. But so K is the K nearest neighbor for each point in the data set. Then they do a local PCA and find those weights. So the W is a matrix, n by n, n is the number of points, which is obtained by minimizing this sum of squares, where it's like PCA, except that those Wij are 0 if you're not one of the K nearest neighbor of point I. Okay, so basically you do a local PCA looking only at the K nearest neighbor of point of each point. Then you try to optimally reconstruct Y in an embedding space of dimension D, and again they have to try different values of D as a weighted sum of the original Yi's. Notice that here there's an explanatory variable Y, and there are there's a Y that we want to predict, and there are X's that we want to explain. So it's a slightly different setting from ours. But the important thing is that you have to choose K and you have to choose D. So we looked at this paper, which is very well cited, and we said, well, we do have a way to choose D, the intrinsic dimension of the data. So instead of trying blindly or projecting in different or reconstructing Y in different dimensions, look around D, which is the intrinsic dimension. And what about choosing K? Well, to choose K, there is a paper, Journal of Chemical Theory and Computation, 2018, that compares for increasing value of K, okay, which for us is N2, the K nearest neighbor, the maximum likelihood estimator of 2 models. So it does a maximum likelihood ratio test of model 1, where we assume that the density of point I and the density of its K plus 1 nearest neighbor are different. So at K, we change density, versus the alternative that the density of point I and its K plus 1 nearest neighbor are the same. So for each value of K, you do a likelihood ratio test, comparing the assumption that the density changes at K or the density does not change at K. So you keep increasing values of K, you test this assumption until you reject the null hypothesis, which is the density does not change. And that is the value of K star. Okay. So with this value of K star, first of all, we come up with the grid star. And because we do this hypothesis testing for each point I, and so we have the largest value of N2 that we can use without violating the local homogeneity assumption, first. Second, we can revise local linear embedding because local linear embedding will be able to locally linearly approximate the function that takes the points in the capital D space down to the lowercase d space. Okay, and this is a function that so far we can not approximate. We don't know what it is. But in many settings, it's very useful to know. Okay, so you're telling me that the embedding space capital D can be projected down to lowercase d, but what is the function that does this projection? So we are thinking about using local linear embedding to find this function and revising local linear embedding with a known value of D and a known value of K. Very ongoing research. If you have better ideas of how to reconstruct this function, I'll be very happy to talk to you. Okay, so the very last application I want to tell you about, and this will take a couple of minutes and then I'm happy to answer further questions, is a paper that I did not co-author, but I think it's very interesting. It was published in 2019 in Advances of NIPS. So what the authors did, and those are again the authors from Sissa, the physicists, which are, by the way, also the authors of this paper. Okay, so they did this, and they did this also application in a sense. So what they did is they studied the intrinsic dimension of the data representation of a convolutional neural network. So the intrinsic dimension in this setting is the minimum number of parameters needed to describe a certain representation. So in a convolutional neural network, for those of you who are in this field, has many layers, and each layer comes up with a representation, or can be thought of as a representation of the input data. And they see that across layers, the intrinsic dimension first increases and then progressively decreases in the final layers. And moreover, the intrinsic dimension of the last hidden layer is a predictor of the classification accuracy of the convolutional neural network on a test set. And they did this on CNN used to classify images. And these results are not true for an untrained network or for a network that is trained on randomized labels, so where there's no content in the data. So the conclusion of this paper is that neural networks that can generalize well, that have a good predicting ability, are those that transform the data into low-dimensional embedding space. But the final embedding space is not necessarily a flat manifold, because this intrinsic dimension methodology does everything possibly in a nonlinear fashion. And this conclusion can give guidelines on selecting the architecture of a neural network or the training procedure. So let me show you a picture from the paper. So first of all, two nearest neighbor, they use two nearest neighbor because 2NN, not NNN. Because at that time we only had the two nearest neighbor estimator, which runs fairly fast. So they could do this on the different layers. So given a layer L in a deep neural network and an individual data point, this point is mapped into the set of activation of the units in that layer. So they used standard convolutional neural network architecture, pre-trained on ImageNet. And then what they see is that regardless of the architecture that they use, the intrinsic dimension first goes up, then it possibly reaches a plateau and then goes down. And what's interesting is that they all go down to a value that is lower to the one of the first layer, and they all go down to the same intrinsic dimension. And I think this is interesting as a result per se. So if you want, this is an application of intrinsic dimension to the structure of a deep neural network that has interesting insights. So if you want to try to use intrinsic dimension either on a real data set or on your favorite deep neural network architecture, we have good news because we have an R package that was done by Francesco Denti. Is now the paper accepted in the Journal of Statistical Software. And we also have Python code. So the Python code suite is maintained by the physicist. We as statisticians prefer R. And then I'm done. These are the path to Hidalgo. So everything started off with a paper in Science that was concerned with clustering. And in that paper, they had a methodology where you needed to know the intrinsic dimension. And so then we had a series of scientific reports paper, 17, 20, 22, and 23. And some interesting applications like the one to NBA data, Annals of Applied Statistics 2022. And yeah, this is it. Thank you. And as I said, now again, the thesis is published in Physical Library, the discrete version of what I've told you about. So there's a discrete counterpart. So if your data is discrete, you should use their estimator. which is actually, I mean, our estimate is fairly robust for mixed type of data, continuous and discrete. But if you have only discrete data, that's what you should use. Yeah. Any questions?
I had a question. You were showing me examples for the, poorly identified model.
Yes.
And you have the intrinsic dimension of 5 for the well-identified one, and then you have 2 for the one because you have like 2 free parameters. So are those results showing the infinite or like a lot of data limit for the 2 case and not much data for the 5 case?
No. Yes. So the question is for those 2 models. Yes, we have that the intrinsic dimension for the well-identified case is 5, which corresponds to the number of parameters, which are all well identified by this data set. On the other hand, for the ill-posed model, the intrinsic dimension is 2. So those 2 models were, the parameter of those 2 models were estimated with the same number of data points. Okay, yeah, so yes.
So if I think about, not infinite data points, and I try and picture the posterior for the poorly identified model, I would imagine it as being 5-dimensional, but 2 dimensions would be a lot more free than the
exactly.
Others. So is it
yes.
kind of picking up and treating the others as noise?
Yes. So the question is, if I want to visualize the posterior distribution of the non-well identified model, yes, what you will see is that it still lives in a 5-dimensional space, but there are 2 of the dimensions, or for example, that have a much higher variability because the prior there is flat and it's almost flat and the likelihood is flat. So the posterior will have a lot of variability there. So yes, so here the intrinsic dimension in a sense translates in variance of the posterior distribution. So that's what you're picking up.
I guess I just had another quick question. At the start, you were talking about all of this is based on your nearest neighbor things where you can pick any metric.
Yes.
So what metric has generally been used here?
Euclidean.
Yeah. Okay.
Because we are on a continuous setting.
Yeah, and like you talked about
Euclidean metric.
Standardizing the data beforehand. I assume that's from like whitening it, things like that.
Sorry, say it again.
Like steering it or whitening it.
Yes, whitening it.
Yeah.
Yes.
So just because the question before about invariances, there might be ways to make it more invariant by changing the metric and probably doing like Mahalanobis is equivalent to whitening inverse or something like that.
Yes. So yes. So very interesting question. So standardizing the data in a sense corresponds to selecting a different metric because the metric can itself standardize, right? So the standardization can be embedded in the metric. So this is something that has to be handled with care because in this case, because what you care about is, and what you pick up is the highest variability of some of the parameters, which are the ones that are not well identified. Here, we wouldn't standardize anything before running the intrinsic dimension methodology.
Yeah, sure. Yeah.
Yes.
So that probably means the optimal choice of metric is also kind of context specific.
It is context specific. Yes, the optimal choice of metric. Yes, it is context specific. Yeah.
But that's a good point because often you might just be chasing invariances without thinking about what you actually want to get.
Yes. Yeah.
Yeah.
Thanks. Very good point.
I thought that was your point.
Well,
but it was a good point.
Okay, thank you. Okay, that we're conscious of time, and I know there's a couple of other questions, but we will leave them. And people, please follow up with Antonietta if you would like to discuss this further. I think that she has some interesting comments to make on this, so maybe after we catch up, I know that Rob is probably the same. So thank you, Brody. Maybe we can follow up.
Sorry.
Some of those points as well. No, that's perfect. So please, and also the same for people online too, if you would like to follow up, then please do so. But we are out of time, so let's thank Antonietta again.
Thank you for the very interesting questions and for the invitation to be here and talk about it.